In the big Bilge Tank, we'll keep you in the know. In the big Bilge Tank, we'll fix your techie woes. Then we'll break the gum, we'll make you still all together raking. And we'll raise a cup of grog down in the big Bilge Tank. In the big Bilge Tank, come and join our fire crew. In the big Bilge Tank, we will show you what to do. And we'll hack it till we crack it. And we'll tell the world about it and forget to tidy up. That's why it's now a Bilge Tank.
Hello, and welcome to episode 021. Is it 021 or 021?
Oh, I don't know, it depends which side of the ocean you are.
021 of the Bilge Tank from Sheffield on Sea.
Aye.
Yar. Today we're going to take a slightly different angle. We're just going to have a look at some ADCs. We're going to talk about ADCs, discuss the caveats, what you'd use them for, how you'd use them with your Pi or your Arduino, all that kind of stuff.
Yeah, a few use cases and answer your questions again.
Always with the questions.
Yeah, always with the questions. So, do we start with the really basic stuff?
Well, should we talk about why you might want to use an ADC? I mean, the world around us is analog, right? So every time your system wants to kind of interface with the environment, read light levels or temperatures or volumes, those kind of inputs arrive at your system as an analog signal.
The world is dirty and analog, yes.
Yeah, and full of noise.
Even digital
horrible
is
noise. Even digital is analog, indeed. So ADCs are a very fundamental part of a lot of systems, especially ones that interface with the environment, because you need to be able to convert that data into something meaningful to a computer.
Yeah, computers these days, very digital. Analog computers went out probably, 100 years ago now.
Yeah, they kind of barely existed, really, didn't they? In the scope of computing as a thing. So, ADCs are really critical. So critical there are none on the Raspberry Pi, but there's plenty of ways to fix that.
Well, the world is so digital that the Raspberry Pi just assumes digital. So digital cameras, digital everything.
Well, it's definitely kind of harks back to the SOC being for a mobile phone. They're not going to be using things like LDRs or thermistors or whatever.
On the squared C bus, so
yeah, exactly. They'll be integrated into the
they'll
digital
have their
package.
own ADC conversions and they'll do it.
Yeah.
I don't know why.
ADC Sunday, not ACDCs. That's something else.
And not ABCs either.
Yeah. ADC stands for analog to digital converter. So fundamentally, it takes an analog signal, so something like a audio wave or a measurement of light, which is discrete at small enough levels, but not meaningfully for most things.
Yep.
And outputs a number, depending on the
binary representation,
the range of the ADC,
ones and zeros,
that can be read in to your system, so that you can actually take a reading. The key factors with ADCs tend to be the sampling rate, so how quickly you can get new readings out of it.
Yep.
The resolution, which is the number of bits that the output has. So you might get like an 8-bit ADC, and that'll give you numbers between 0 and 255. Or if you get a 16-bit ADC, that'll give you numbers between 0 and 65,535. And that kind of what you want to do with your system depends a lot on the specs of the ADC you want to
and there are trade-offs
use
as well between things like sample rate and accuracy. So
there
the faster
is.
you sample, the less accurate you'll be because it just doesn't get time to saturate those last bits.
Yeah. And you can do things like multi-sampling. So you can take, say, 10 measurements and then average the results. So you can actually increase the resolution of your ADC by slowing down your measurement speed by taking multiple measurements and combining them into one. So there's a lot of trade-offs. They're not hard to work with, but when you get in depth with it, there's a lot to consider.
Nuances.
Yeah. But for most people, like most AVRs and like little add-on boards and things, they tend to be 8-bit ADCs because they're the cheapest.
Does
so
the
they can
Atmega 328 a 10-bit?
I think certainly the X-Maker, I'm sure, is 10-bit. I don't know if 328 is.
I'm sure.
Is it 10-bit? Possibly.
I was reading it was one of the Atmegas that you had a 10-bit ADC, but you could clock it right up to 1 megahertz and just discard the 2 upper bits. So that you got a really nice, fast 8-bit ADC.
That does ring a bell.
It's handy for audio processing and things like that. Which people do on the little Atmega.
Mm-hmm.
Oh, we got data sheets.
ADC resolution is 10 bits. You are the winner, Phil.
I am the winner.
And on our Explorer hat, we use the ADS1015, which is actually quite a high quality ADC for the kind of uses it will be used on the Explorer hat. It's actually a 12-bit ADC. Yeah. Well, yeah, but 12-bit ADC is nice. You know, you get a good range on that. You get 0 to 4095, that gives you a lot of really little discrete steps, which is, it's nice. It's good stuff.
Yeah.
So I guess we've set up a breadboard here that actually has like a discrete implementation of an ADC. It's only 3 bits, which basically means it can give you values between 0 and 7. The reason it's only 3 bits is that essentially for every bit of information that you add, you need to double the component count. So this takes basically 8 copies of exactly the same circuit. Each copy is giving you a single value in the range, basically from 0 to 7. And obviously that range of 0 to 7 then translates into 3 bits of data, because you can represent 8 steps. But it's kind of cool. It's an interesting approach. This is kind of like what you'd call a parallel ADC. So essentially it uses if we can see better on camera.
Got the other camera to point down at it.
Hey, look at that.
There we
Wow,
go.
I've got a pointy stick also. So the key, that's beautiful. Which way? That way.
Just made it
Oh, it's really nightmare to work out. That way?
Wait, where are you trying to put it?
I'm trying to move it not like that. Oh, God. Yeah, there we go. Brilliant.
Hey.
Okay, so the key feature of this is that it's entirely basically done with op amps, so or comparators. So with a comparator, you have 2 inputs, and you can put 2 voltages into it, and the output will tell you whether input A is higher than input B, or vice versa. So if we put in, say, 2 volts into the positive terminal of the comparator, and we put in, if we put 2 volts into the positive terminal of the comparator, and 3 volts into the negative terminal of the comparator, then our output will be low, and the other way around it will be high.
So it's as simple as that.
It's
That's
very, very
one bit
basic.
of resolution.
That is a bit of resolution.
In fact, it's no resolution really, because it's just which one of these is higher. It's
Yeah.
almost logic.
So you can actually make an
Almost.
ADC with that, where you set your reference voltage at 2.5 volts, say on a 5-volt circuit, have a single comparator, and if the voltage is higher than 2.5
So you've got
volts,
0 and 5 volts here.
and 2.5 volts right there. This is
Yep.
brilliant.
So Phil,
Scrap
your
the
signal.
whiteboard idea.
Signal.
Yeah, brilliant. Nice signal work. So when the signal is compared, the output will actually slam down to 0 or up to VCC, essentially, down to ground, up to VCC. And that means that you can tell whether the voltage is above or below the voltage you're currently sampling.
So that, if you were doing something like measuring a light level and you wanted to do it entirely in discrete logic, for example, you could use a comparator and use that against the reference voltage. Say if my light sensor reference voltage is higher than the reference voltage, then output 1.
Absolutely,
and turn on
yeah.
a light or something to that effect, or lower in this case.
And you can tune your trigger by setting that reference voltage, so you can increase it to make the light level have to be higher, or decrease it to make it lower. What we've got here is we've actually set up kind of an array of resistors. So this is basically a massive potential divider, and we just tap off at each point. So there's actually 9 resistors in here, and that's just because I don't want a tap-off point at either end, because you're not going to go over 5 volts on a 5-volt system. You're only ever going to reach it.
So they're all the same value then?
They're all 1K, which makes this a linear ADC, because if we took the multimeter now and we measured across, if we imagine that was 10 volts, 10 volts across the whole set,
Yeah.
which it isn't, but if it were, you'd essentially read roughly 1 volt, 2 volt, 3 volt, 4 volt as you stepped up the ladder. And that means that we've got we've actually got 8 discrete increments of voltage, and that gives us our resolution essentially on the ADC. So where I was holding the pen up saying that's 2.5 volts, and Paul was like at VCC and ground, on ours we've got 8 pens.
8 pens.
All the way in between.
Man.
So your 2.5 volts might be
we're
somewhere in the
octo
middle there.
Here we go.
We really. Oh wow! Yeah. Okay. That is exactly 8 pens. Brilliant.
There we go.
We really should have had a diagram for that. That would have been useful.
Hey, it wouldn't have ball pens.
But that means that we have these like 8 reference voltages now, and they are basically the triggers that we have to say whether we've gone, our discrete steps in the ADC.
Right.
And then the 2 chips to the side, which are just here, back into movement hell. We have 2 chips, and they're both quad comparators. So basically, each of those chips contains 4 comparators. So it's a lot more compact than using, 8 individual comparators. We just feed the reference voltage into each comparator. One of these reference voltages into each comparator, and then our signal voltage, which is actually, we've got it coming from a waveform generator, which is generating a 1 Hertz sine wave with 3.3 volt peak to peak, because we're actually running on 3v3 here. Our reference comes from the waveform generator, our measurement signal, the signal we're actually trying to measure, and that is just linked directly between the other inputs on the comparators. There's no other discrete circuitry there, they are literally all just tied together, because we want to compare that analog signal against all of our 8 references simultaneously.
Yep.
And then the comparator outputs are just mapped over to LEDs, so there's nothing particularly complicated here, but each LED's got a current limiting resistor, just because we're sensible like that, and a pull-up resistor as well, which the comparator outputs need a pull-up on them. But there you can see the 8 discrete steps of the ADC working, and what we're actually feeding in is a perfect sine wave. So you can see how the system breaks that analog signal down into discrete digital kind of chunks, basically.
So something that looks like that on the oscilloscope actually ends up looking on the LEDs like a set of stairs going up and down.
Exactly that. And in this case, it's like a sine wavy one, so it slightly flattens at the top and at the bottom. But yeah, if we made it like a sawtooth, it would just be a stair step up, stair step down. Most systems, obviously, this information, the way this is being output, is basically saying which of each of the incremental steps is turned on at any given moment, which isn't very usul for a digital system.
So that's not actually the 3 bits, though, is it?
Well, it should be 8 LEDs, but I ran out of space on the breadboard. So there's 7. There's actually a dangling lead here for the 8th LED. But basically, you would need to then encode that into your binary.
Okay, so we're not binary yet. What we've got is analog to digital, so we've got discrete readings now.
We now have logic level discrete readings that we could then convert into a binary kind of representation, essentially.
Yeah.
And you can actually do that using a load of diodes and stuff if you want to, or you can use like an encoder basically that has 8 inputs and give you a 3-bit output. Those are chips that are available. But yeah, that's basically how a parallel ADC works.
Right.
The main downside with these is obviously normally you would always buy an ADC in a chip, because why on earth would you do all that when you can just stick a little chip on? But obviously for this, every discrete value we've had to add a whole separate comparator circuit.
Yep.
So you can imagine that like a 16-bit ADC that has 0 to 65,535 as its value range, you basically need to scale this out that many times.
Really?
Yeah, you need 2,000 times as much of this to represent that, basically.
How does that fit in a chip, John?
Well, I don't know whether they actually make parallel ADCs that big, to be honest, because a lot of the stuff we see these days is Delta Sigma, but that's the fundamental of how it works, so in principle that's what you'd have to do.
Okay, so early stuff was parallel ADC.
I don't know the history accurately.
Okay.
So I'm not saying it's early.
So Delta Sigma? You've just dropped that in there like a bomb.
I don't even want to go there. It's very clever, but more complicated. Though, having said that, if you're interested in how Delta Sigma ADCs work, the Signal Path blog has a really great YouTube video on it. But basically, the way that Delta Sigmas work is they, instead of having these kind of multiple parallel circuits all evaluating a different discrete level, they have like a stream of data. It's run on a clock, so you have a sampling frequency, and what happens is that the output is actually fed back into the input, and the difference, the delta, is calculated between the input and the current output. And what that causes it to do is essentially kind of flip-flop internally, and it just gets this stream of ones and zeros, and they then go into an integrator, which is the sigma part, which basically adds up all those values for a specific chunk. So for, say, 1024 clock cycles or whatever, it sees how many ones and how many zeros it got. That gives it a value and says for that sampling period the value is X. Just because of the nature of the way that circuit's set up, it's very clever. Watch the guy. Signal Path blog. He's excellent.
Is
he knows his stuff.
The same as successive approximation?
No idea.
Successive approximation, where you're basically kind of doing a binary search on the ADC value.
You can see how that would work, wouldn't it? I mean, I suppose you could. Didn't read anything about that.
The other way that's not used very often that I read about is where you have a decade counter or an 8-bit counter, and you have a resistor ladder coming off that 8-bit counter that has various different resistance values, and you run that 8-bit counter and it produces all the voltage ranges possible between your ground voltage and your maximum measurement voltage.
Okay.
And then you take your input voltage and you keep comparing it, you keep comparing it, you keep comparing it, and then at the point that when they're equal, you say, aha! And the value that's then in your counter is the value
is the correct value.
Your ADC value, which means you've got to constantly be running this counter round and round and round in order to do the comparison. But
I suppose that's not necessarily...
It's not entirely mad. It's a very ingenious solution to
Well, similar to the Sigma Delta,
Clock, yeah.
it has to clock a certain amount of data to understand it. This one's kind of interesting because it's instant. I mean, as fast as your op-amps function, basically. But all of the, it takes all the inputs data and produces all the outputs data in one shot. There's no kind of staged pipeline of processing or anything.
So can we start messing with the frequency? See what happens with the sine wave?
Yeah, of course we can. So at the moment I've set it up. Something slightly interesting with op-amps comparators, quite often the voltages, the kind of logic voltages we work with tend to be lower than the rail voltages. It depends on the part and there are certain limitations. But that means that what I'm actually doing is running all the logic at 3v3 on here, but supplying the comparators at 5 volts, which is a great opportunity to advertise this beauty at the end, which is a breadboard power supply from Seed. It actually gives you a 3v3 rail on the top and a 5v5 on the bottom, which is so handy. And obviously it clamps onto standard breadboards, but that was so handy for this because I needed those two supplies simultaneously, which was very cool. But basically, yes, I can shift the offset. So at the moment we're offset by 1 volt.
John's on in beautiful detail.
Whoa! So there, we've just moved the offset up. So now our sine wave is basically a little bit higher. So we're never hitting. These LEDs are inverted, by the way. So the on is actually 0, and because they're syncing into the comparators.
Live circuit
What are you doing, Phil?
Circuit bending.
Madman.
What are you doing, Phil?
Oh, you're just going to set it up to use the...
Taking over your ADC, man.
That's alright.
Yeah. So I want to use your ADC to measure the value of my little potentiometer. Oh, you can go straight in.
Tap it in there.
Oh, there we go.
There you go.
So now...
So Phil's just hooked up a potentiometer between the 3v3 rail and ground, and we've connected the wiper directly to the input of the ADC. So
this
as
is
he
great
turns
because
it,
you can feel
turn the
just
LEDs
how
on.
big each step is and just how low resolution it actually
I'm
is.
just going to emulate the 8th LED going on. But it's not physically there.
That's amazing. And
Okay.
you can feel the stepping a lot more when you actually turn. Obviously, you have to rely on my explanation here, but when I'm turning it, I can actually feel.
It's properly
different
discrete,
distance
right?
that it's turning. Yeah.
Yeah, it's not like the LEDs are fading in bit by bit. This is logic on or logic off. It gives you a snapshot of the current analog
It's
value
actually a
going
really cool little circuit to build up for kind of educational purposes. Maybe we should turn this into a kit.
It's an absolute nightmare to breadboard. Would never do it
It's
again.
not that bad. I mean, look at that. That's pretty
Yeah, I
straightforward.
know. That's a third build.
The most yeah,
It's quite tidy now.
Well, now you've figured out how to do it, we can put that in schematic
tell
and
people
make it
how
quite
to.
easy.
Let's see if we can get anything out of this amplifier.
Oh, that amplifier confuses me slightly, but...
In principle, this should just be a nice... There you go. Woo!
Hey, woohoo! Can you see that? Oh, you're going to clap. There we go.
Okay.
So you could
fully
do...
discrete clap sensor. There's no microcontroller in there at all.
Yeah, basically. And again, like Phil was saying, the thing about this being linear resistors here means that we've got a linear ADC. There's no need for that to be linear. You could make this logarithmic, and it depends on your purpose really. If you want, so here, quite interestingly, with the audio one, you can tell there's like a baseline, like halfway roughly is some sort of baseline noise it's picking up, and only by tapping it do we actually peak. But if we tweak those resistor values, we can make it much more sensitive to certain areas.
Yeah, so instead of going, say we had between 0 and 100 volts, instead of it going 0, 10, 20, 30, 40, 50, you'd have it going 0, 1, 2, 4, 8, 16, 32.
Yeah, exponential or whatever, something like that.
Which for noise is really good.
It is. But yeah, you'd never build one like this. You can actually buy non-linear ADCs, but I think they're less common. I don't know.
You'll build one if you were trying to learn about it, and I think if you took the LEDs and you made them sort of green, yellow, and then red, and then did your clap sense thing, you'd have a really nice kind of little audio VU meter.
You would,
Just tiny discrete. Which is a fun little thing to play with.
It is a fun little thing to play with.
So next step up, actual ADCs in use.
Yeah, well, then obviously that's roughly how it works, but if you want to put it into your project, you're almost certainly going to use either a breakout board or like a DIP chip package. We sell a microchip parts, I think. Yeah, MCP 3004, which is a very popular ADC chip hobbyist. That's basically a 10-bit ADC with an SPI interface. So you don't have to do any crazy messing around. You just
So SPI, perfect for Arduino, perfect for Pi.
Yep. The SPI, Arduino and Pi both have SPI interfaces. SPI is nice because you can drive more than one device at a time. It has like a chip select feature.
Okay.
So You can kind of round robin different chips. If you need more than 4 channels, you'd probably buy the MCP3008, but you could in principle put 2 chips down and use chip select to switch between which one you want to talk to. Things like this are nice because I haven't used this one very often. I tend to use our breakout boards, but usually they'll carry on sampling in the background. So obviously you just go and talk to it when you want to take a reading out. Or some of them I think you can say start a reading now, and then you get like a trigger warning or something to say it's ready.
We'll have a
pull
little
your data
interrupt
out.
pin that says conversion complete, conversion complete, conversion complete. You drop in and go, oh, I have my data now.
But microchip generally we quite like because they do so many of their parts still in DIP package, which is pretty rare these days. There's a lot of places are moving to SNT only, which is a shame.
We've got the data sheet here. Let's take a walk through the data sheet.
Just take it, pop up. Go full screen, Paul.
You say you have an interrupt on your ADC where it'll tell you that it's got a value. That's interesting what we use in the Flotilla modules when we're reading ADC values. It will start a reading and then it will go off and do something else.
Like talk I2C to the dock.
Talk I2C to the dock, yeah. And then when the ADC has completed its conversion, which obviously takes a period of time depending on how fast you're driving it, what frequency you're running it at, it will notify the PIC, and the PIC will go, aha, value now, and then it can stop what it's doing, grab that value,
quickly slurp it in,
and then carry on and leave the ADC to continue its thing. So you don't have to be overly attentive with ADCs. You don't have to constantly be going, you got the value yet, you got the value yet, you got the value yet, because it's painful if you do it that way.
Yeah.
Right. So what's the spec on this?
This is basically a 10-bit ADC, and as we said before, you talk to it via SPI interface. I mean, there are a lot of different kind of specs you get. This is 200 kilosamples per second at 5 volt VDD, but you basically need to read the data sheet. It will show you'll get a load of graphs basically that will tell you the characteristics of it under different situations. So like whether it's what voltage it's running at and all sorts of things like that, sample rates that you can get out of it.
So that's 200,000 samples a second at 10 bits. Sounds pretty good.
I don't know if that sample is actually a single bit, or I'm not sure what technology this one uses. It's a successive approximation, which is the one that Phil was talking about.
Yep.
Let's have a look.
So samples, you think it's got to be the voltage, right?
Capable of conversion rates of up to 200 kilosamples per second.
So you've got to have a SPI bus that can take that in.
Well, it doesn't. You don't have to read it that fast. So obviously you can only take samples as you need them, but I guess that's the kind of the limit.
So when you're looking at things like this, let's say we wanted to sample kind of audio in the human range. So the human range of hearing is somewhere between like 20 hertz at best. So that's a really big Bose rumble, like a subwoofer. And then it's up to about 20,000 kilohertz. So this
20
sounds...
kilohertz.
Sorry, 20 kilohertz.
20 kilohertz.
Yeah, 20 kilohertz, 20,000 hertz. That sounds like this could do audio sampling.
I imagine so. I don't really do anything with audio, so I don't know. But
so the rule of thumb, not even the rule of thumb, when you want to sample something at a certain rate, you want to look at the Nyquist frequency, which is double the most significant frequency, the highest frequency you want to listen to. So if you're looking at audio, 20 kilohertz, we need an ADC that can sample at least 40 kilohertz.
Yeah, because you don't want to. If it was just like a sawtooth at that frequency, you could miss every single peak, right?
Yeah.
And only get the twice. But if you get twice the sample rate, you're going to get enough data to reconstruct the original signal accurately enough.
Let's look at that. So we've got the 1 hertz thing where it's going, the sine wave is going woo, woo, woo. Now if you were sampling that once per second, you could always hit it when it's going woo. So you can sample it woo, woo, woo. And you'd assume that was always at the top level. You would assume
like
that was always high.
Signal, basically. Yeah.
Therefore, you're getting a really false impression of what the analog thing you're sampling. So that's why you need a frequency that's suitable for the signal you're looking at. I think the high-end version of that is things like an oscilloscope, which can sample up to 1 gigasamples a second. That's 1 million samples every second. That's pretty high bandwidth, so it can sample pretty fast signals.
Yeah, we'll have to have a play with this part specifically, and see what we can get it to do that's kind of interesting. But obviously you need a system, because working with, say, an Arduino, it'd be quite hard to accept that amount of data, just because you've got such a small amount of memory, such a low kind of processor power.
Yeah.
But stuff like Raspberry Pi, you could easily slurp in that kind of data rate and do meaningful things with it.
Yep.
Which is kind of cool. Yeah.
So if you're looking at, say, a sound card on a PC, the mic in, that's essentially an ADC.
An ADC.
Yeah.
Yeah, we've got Michael correcting you as well.
Huh?
Max is 22 kilohertz.
Yeah, it depends on the ears. We're just working,
It depends on you.
working with easy numbers here.
We got very bad ears.
We're building robot ears. We can build bad robot ears if we want to.
Yep. So we've got that one that does 200 kilosamples a second max.
Mm-hmm.
That's at 5 volts. What else have we got in there that's of interest to us? So what's this LSB stuff?
Well, that's the least significant bit, isn't it? So I guess it's going to be something to do with differential non-linearity, it says there. Not even touching that. Yeah, I don't know. I don't use
that's kind of
ADCs that much to really know how to read much into that, to be honest.
So that means you're going to lose a bit, maybe, of resolution.
It looks
worst case
like it's something like that.
So this is stuff where we really wish we were electronic engineers.
Yeah, well, it's the kind of thing where if you need to know it, you can go and find this stuff out. But if it's not something you bump against, we tend to use ADCs for kind of hobbyist stuff, so things like light sensors or this audio input. That's where they're primarily useful for us. Servos for getting the feedback as well, so that you can measure the position of a servo and stuff like that. So they're much easier to use than this datasheet suggests for most uses. It is basically just a way to sample some sort of analog value from the outside and turn it into something you can write code against.
Datasheets can be very, very scary.
Datasheets can be scary. You just got. I think most of the time you got to know what to ignore, or what bits matter to you, basically. But for most uses that we'd use, this would be perfectly appropriate, and it would be easy to set up and easy to talk to. On the Explorer hat, we've got the ADS 1015, which is really nice ADC, and obviously we've got all the code libraries for that there. I think you've got an LDR hooked up there, Phil.
I have.
It
works quite nicely.
I've got your Pi over here.
Oh,
in your Pi.
Aha! You have just type Python.
All right.
And then import Explorer hat. And then read me an analog value of Explorer hat.analog.1.read.
Explorer hat.analog.1.1.
One the word, sorry.
Boom.
Oh, there we go.
3.975 volts.
Let's cover it over.
2.78. See, that's how easy it is. So basically, as much light as is entering that sensor is mapped.
So I have no idea what this light sensor is, so I picked a fairly arbitrary
10K.
resistor value. I think I've got 22k on there. I had 10k.
Okay. So it'd be a bit unbalanced. I've got some 10k resistors here.
So you were sampling about 1 hertz there. You were taking a sample every second.
Yeah, something like that.
Just for comparison.
So if I were doing this at about 1 hertz and John was measuring about 1 hertz,
I'm missing it on purpose now.
he will miss it basically.
Look, it looks really nice and bright in this room. There's no idiot's waving his hand over me at all. Oh, wait a minute.
But now if I hold my hand, you'll get the lower reading.
Yeah.
Which just demonstrates what Paul was trying to explain in the real world.
Most of these analog kind of sensors, you set them up as a potential divider. So this LDR is almost certainly a 10k LDR. What that means is that you'll generally put the LDR in series with a 10k resistor and then take your measurement from the middle. Looks like bullhorns.
I can't point it down.
Sorry. But yeah, so normal, an easy mistake to make is just plug in the sensor and think it's going to do something. It's not. All that happens is that the sensor's internal resistance will change as it's affected by the analog source that it's measuring. So like with the light sensor, as I cover it up, I think the resistance gets greater, but I'm not 100% sure. One or the other. And it's that changing resistance in combination with the fixed resistance that that lets you actually tap off like a meaningful signal.
Effectively creating a voltage divider with 1/2 of the voltage divider being variable.
Yeah, basically, exactly that. So normally you'd have something, part of the spec of this sensor would be that's 10k, so you'd probably match it with a 10k resistor, so it's a reasonable choice. Then roughly your scale will be, you'll get a decent range out of the readings at that point.
So the reason for that is, on these microcontrollers we have voltage readers, things that can read voltage.
That's the ADCs, yeah.
Yeah, if we had a multimeter, we could read the resistance of the LDR directly, couldn't we?
Yeah, we can
But
do
that's,
that.
yeah.
We can do that right now.
But that's impractical to do on a microcontroller, because you don't want something this size.
Do you want to put the crop clip ends back on?
Oh yeah, that would be good. Clips on there.
So because we read voltage, we use the voltage divider to turn the resistance into something we can actually read.
Hold on, I'm going to bend the legs up so it gets
Lively.
contact. Oh, clamp me.
Clamped. Right, so let's bring that up. Have a look on the screen.
Some more. So we're reading about 4K.
4 kiloohms at the moment.
I bet we've got a lot of glare on the screen.
Turn the backlight on, maybe.
Oh,
Oh, lovely.
So we've got 4. Yeah, it's basically the LDR is currently reading as if it was a 4 kiloohm resistor, give or take. And if I cover it with my finger, it rescales and it's gone up to 17k.
It's got resistive.
It's gone resistive. So as you basically occlude it and expose it to the light, this auto ranging's not great for that.
How do I turn the auto range off?
The value of this kind of resistor changes, and that combined with your fixed resistor gives you a potential divider.
Hand make a difference with the little scale on the underside now.
Beautiful.
So this is sampling pretty quickly on that meter at the bottom, but the digital meters update more slowly.
I would imagine that the numerical one is going to be a more accurate reading, and that maybe the graph is just tapped up at a lower resolution or something, perhaps.
Yeah. Cool. And James is tapping in from the hospital. Wow, James, don't break yourself. Hopefully he's not been messing with mains voltage or something. Yeah, get well soon, James. We want you to be healthy for the Pi birthday.
Definitely.
Yeah. Okay, so there's some futzing about with...
there we go, manual range 5K.
Yeah, and there's lots of these these analog sensors that you can get, and they're super cheap. You know, like this LDR will be like 10p or something. They're ridiculously cheap. But things like light-dependent resistors, you've got potentiometers, obviously, so that's nice for making interfaces.
Yep.
You've got thermistors for measuring heat. You've got things like photo transistors. There's all sorts of different sensors that you can use with this method. You just hook them up to an ADC, read the values out. Most modern sensors now have the ADC integrated, so light sensors will have a built-in ADC and they'll have the I2C interface kind of implementation inside, but they're almost always surface mount only. So for hobbyists, it's much easier to hook up something like this.
But that leads on to the Flotilla things you've got there.
It does indeed. So these are actually not ADCs, but PIC microcontrollers that we have basically told to do nothing but pretend to be an I2C ADC that reads the channels we want it to. So for the joystick, we're actually reading an X and a Y channel
and a button
as
press.
analog inputs and a button press, of course, as well. And we're using the PIC and using the interrupt feature of the PIC again, as I was explaining earlier, to basically trigger the ADC conversion, go off and do communication with the Flotilla host, and then when the conversion's finished, it will get the number out of the ADC part of the PIC. It will convert it into whatever internal number it needs, which sorry, I've got a pretty groggy throat for some reason.
Me too.
It will convert it into kind of the Flotilla's internal scaling, so it takes that number. I think it chops off the two least significant bits because we don't really want it to flap around too much when you're using a joystick. You don't want it to be kind of wavy. And then it also does some very basic kind of averaging. So as you move the stick around, it will average the last few values, which are happening so quickly that you won't ever feel that that's happening.
No, it just stops it fluttering, doesn't it?
It does, yeah, it just keeps out.
If basically one of the caveats of an ADC is that because it splits into discrete levels, if you're right on the threshold of a discrete level, very, very small fluctuations in the kind of input signal can cause you to jump backwards and forwards between that kind of discrete value. Yep. With something like the joystick, that means that you'll end up getting a reading that's like 90, 91, 90, 91, 90, 91. So we do a little bit of averaging over a period of time.
I think we had some earlier Flotilla modules that had an actual ADC on board, didn't
Yes, but the perverse thing was the ADC cost 3 times as much as the PIC microcontroller.
Yeah, you can take a microcontroller and you can program it to do whatever you want and add smoothing and all sorts of intelligence into it, and it can be cheaper than ADC.
Yeah, crazy.
Yeah,
it's a bit.
Right. What else have we got to look at?
I think that was kind of it. I brought out the Sidekick component kit just because I was using it to build up the circuit. Well, there were two things actually, because I haven't done much breadboarding for a while, and I was reminded about a couple of things. One, how much I love these jump leads because they're preformed, so they've basically had their wires stripped, and they're just lovely little preformed wires, which is kind of awesome. You get so many different lengths in there.
When I create,
that's not even one of the
boards.
I did. There you go. Show the tray, Phil.
Show the tray.
They're dead handy, and the ends are preformed down. So basically, you just find the wire that's the right length, and I've used them all over this breadboard. It saves you having to strip and
they're bent to the steps of the breadboard, aren't they specifically?
But basically, yeah, you can pretty much always find exactly the wire you want just to keep it flat against the surface. Otherwise, you end up with like Franken circuit and wires hanging out all over the place. And the other thing was that when you are doing breadboarding, always have a nice pair of thin nose pliers, because when you get a component and you trim the leads down, being able to just turn a leg like that is so much easier to get in the breadboard than bending them by hand.
For getting it into the breadboard as well, because
Yeah,
sometimes
you
the
can
breadboard holes
tweak it
will be
in.
quite resistant, and when you're pushing something into the breadboard, you'll end up bending the leads rather than pushing it in. So I tend to use like even those pliers to grab the leg and push it into the breadboard.
Definitely.
So Connor is asking, obviously joystick is good, but can we use things like the Skywriter as an input to Flotilla?
Not at the moment, but in principle it could be.
Well, if you're using Python, yeah. You can
Well,
just use Python.
you could blend the two in your own
Using
projects.
Python, you
Yeah,
can
of
mix and
course.
match.
Yeah.
It's not supported in Rockpool is mainly what I'm saying. So there's no feature for that. It might be something we look at in the future, but we don't know yet.
Could be a Flotilla module theoretically, couldn't it? A very small XYZ.
Could be. It's so horrible to work with though.
It is pretty horrible.
I prefer to use that touchpad that you've been working on,
Yeah.
because I think that's potentially more sane.
And Connor has a follow-up question. Link to buy the jumper leads?
Just search for jumper leads on our store. I'm afraid we don't sell the needle nose pliery things. That wasn't actually a shilling a product thing. That was just, I love these things.
Sometimes we just have
Get
stuff
some.
around.
That normally ends up with us getting some, doesn't it?
It usually
We'll have
does.
some, yeah.
We'll get some. But yeah, the jumper leads, just search for jumper leads. In fact, that's something to say. We've rejigged our entire prototyping section on the website. In fact, let's bring that up. Let's have a quick look just before we go.
In the news.
Because it's dead handy. Can you get us the website up, Paul? Someone emailed me and said, I can't find any components on your website. So I went and had a look and realised that no, you couldn't, because it was kind of awful. So I've reworked all of the categorisation in prototyping. So now if you go to the prototyping section, which is basically prototyping / components, so anything you might want to use in a breadboard or on Vero board or things like that, this section is now much better classified. So if you want to find something like one of those ADC chips,
Hey, there was something for jumper lead there.
I'll find that in a second. So there you go. This is all the ICs that we sell, and we're probably going to add to this range. They're just ones that we tend to have around for stuff.
Trouble
We've
with
got a jumper lead
there's so
section,
many of them.
which gives you like JST jumper wires, jumper jerky. This is the pack jumper lead selection. It's just much easier to browse kind of component style stuff now. Which is good because it was a pain in the ass before. So.
Oh, and if you did need some kind of microcontroller, then back in stock today, or in stock now, Genuino.
I don't think we've put a link on the top yet.
Should be under Arduino Co, shouldn't it, eventually?
Yeah.
So collections / Genuino.
Yeah, we're going to change that header at the top.
So this is kind of the original gangster Arduino dudes have actually, they're having a little legal spat with part of themselves. The end result is that outside of the USA, Genuino is what used to be Massimo and crew. It's Massimo and Tom and all the people you see doing talks at Make Fairs and MakerCon.
Genuino is the EU, the Middle East, and China, I think.
Yeah, they just say outside.
And Canada
USA.
even. Oh, yeah.
Anywhere that's not the USA, yeah.
Pretty much.
Yeah.
That's a very comprehensive list of places that are not American.
It's a lot of places.
Anyway,
So,
this is where the heart is.
yeah, we now stock Genuino. We're waiting the starter kit and the Genuino Micro we should get in February.
Yep.
The rest of them we can get hold of right now. So.
Cool. Including the Genuino 101.
Which is the first Intel Curie based board. Kind of
Yeah.
interesting. We talked about that on the Bilge Tank quite a while back, actually.
Yeah. So what's this got? An x86 Quark.
Yeah, this is
With a
Quark board.
Viper OS real-time operating system.
Yeah, it's
It ain't going to run Windows, but
No.
it's x86 based.
It's got Bluetooth on board, which is quite cute.
Yeah.
All the inputs are 5 volt tolerant, even though the core is actually 3v3. But they've just basically put these buffer chips on there, so that's kind of handy. This is Intel's first foray into the maker world, I guess, in combination with Arduino/Genuino.
So it's an interesting bird, isn't it?
It is quite a lot of flash memory, which is pretty generous. Not a huge number of PWM channels, but it's not bad. And it's got a built-in accelerometer and gyro as well. So that's on the board itself.
That's nice.
It's kind of cool.
You have to chuck an
How much
accelerometer
is
on
it
there
then?
these days.
You do, or it just ain't a thing, is it? But yeah, definitely worth a look. We haven't had a chance to have a real poke around at one of these yet, but they do look interesting.
Yeah. I noticed Adafruit have released their Circuit Playground soon, aren't they? Where they've stuck a load of sensors on something.
That is, we don't have these yet, but we will certainly be looking for them.
But in terms of chucking accelerometers and lots of stuff on something.
Yeah, you're talking about this right here, which is kind of curious. Yeah, we haven't had a good look at it yet, but we'll definitely be bringing some in. It's just a case of when we can get hold of them. But yeah, they've got some nice crop clip pads around the edges. Obviously, lots of blinky LEDs. People love that. Accelerometer, gyro, LiPo power supply option.
Yeah, no price yet,
cool.
but I think they'll make it keen.
Yeah, I don't.
Hopefully.
No, they haven't got a price yet, have they?
Yeah.
So
Near pixels, because
I think these are the
Why not?
35 package ones as well, 3.5mm near pixels rather than the full 50/50s.
Ooh.
They look quite small if you compare them to like the chips and the switches, so I'm pretty sure they're small.
We've got some of those in the house now, haven't we?
We've got a reel of those downstairs. Yeah, we're playing around with them at the moment.
Cool. And what's the micro on this?
I don't know.
Oh, 32U4,
32U4.
so still old school. We're seeing a lot more ARM M0 coming through now, which is interesting.
Michael's asking about Pi Zeros. We literally have no idea. That we'll have them when they arrive. We know nothing more than that.
When John's not in the Bilge Tank, he's waiting by the front door for them.
Pretty much every day. And when can you buy multiple? Well, basically when we manage to get all of our email notifications done, which is in the region of 65,000 or something. So it's going to be a long time.
Remember the original Pi launch? That.
Yeah, I think Pi 2s they still are the mainstream. They're still the most popular, and they're still selling great quantities. So the Zero, it's 1,000 or 2,000 tip up now and again. We put them on the shop as soon as we can. They sell out
straight away.
Yeah.
It's just one of those things. It's a bit frustrating, but now we've just kind of accepted it, and if they turn up, we'll put them on the shop.
Yeah.
Can't say fairer than that.
Everybody should have one to play around with. So we want everybody in the world to have one, and then multiples will probably be available, pretty much.
Yeah.
I think it's just there, it's good. It just stops headlines for the next 4 years of, the $9 computer, the $8 computer, the $7 computer. Let's just cut straight to the chase. $5. Yeah.
Game on.
Cool.
I think that's everything we have for today.
Yeah, thanks for listening to us try to change direction a bit.
I think we'll do a little better next time.
If only we had time.
Although this was amazing, I don't know where you produced this.
It was kind of fun,
you
actually.
were up to something.
What's he doing in there?
I think that needs to be an article. And do we sell these?
In fact, I'll give away a Pi Zero to the first person who builds a 128-bit one of those. See you next week.
Evil.
Someone. No, it's just not going to be worth.
That's like a room full. That's like one of those old computers at Bletchley Park or something. It's like,
you gotta have a couple of a rack-mountable breadboard system first.
I've got one Pi Zero I haven't used on my desk. So
have you?
Somebody in the chat now. What can we do to give away? Ooh, think of something. Anybody got a good question?
They released a pic, did they, James? Could be in store soon. Okay. Find out.
Yeah. I mean, Evan was hinting that some
on
were on
Twitter,
the way.
yeah, there was a whole bunch
You got
of
Palmer Violets?
I do have
Thank
Palmer
you.
Violets.
It's very British of you.
Okay.
I got all the dust.
Oh, no, here's the question. How many Palmer Violets does Phil have left in his packet?
Oh, that's good.
Sorry, after I eat this one.
We're going to be waiting now.
We're not going to be waiting. It's only just so... There are very few discrete values in that packet.
Okay. And we want a digital value.
Yeah, no analog answers, please.
no.
That's it. We should have demonstrated this with sweets. What a mistake to make it.
Well, what is...
So we could have had a lollipop and then the Palmer Violets next to it. That would have been amazing.
Yeah.
Lollipop is kind of analog, licking away at it.
Oh,
and
I
then
see.
Palmer Violets,
It's one at a time. Yeah.
Digital.
Okay.
The
Do you know how many
switch.
Palmer Violets you've got left?
I'm pretty sure.
Yeah.
I'm pretty sure.
Do you want to double check?
Let me double check.
Right, nobody's guessed yet, so...
No one's. I don't think
What's
anyone's
STS stand for? It stands for Space Transportation System, as in the spatial STS.
So spatials are
for
STS.
70 tiny squirrels.
Leo reckons it's 7. Connor Ballard.
Oh,
Pickman reckons
Leo
6.
is the winner.
How did you know
Oh,
7,
How
Leo?
did he get it so quickly?
You're some sort of Palmer Violent
Sir,
savant.
you've been
It's crazy.
counting my Palmer Violet consumption.
Can
So,
you
Leo.
email Phil@Pimmeroni.com?
Yeah, let's make it Phil's problem.
Oh, go
Email
away.
Phil@Pimmeroni.com. We'll sort you
He's
out.
not got enough to do.
I hate you.
Rewriting Rock Ball to be awesome.
Right, that's it. We're done.
Right, thanks folks.
Out of here. Subscribe.
Tune in next week where we'll hopefully be back to Thursday, but
Yeah.
we're not gallivanting about the country.
Indeed. Subscribe.
Comment,
Like.
See you next week.
tell your friends.
Bye.